So this is when we don't have a measurement from the corner. So I'm gonna first start from the center of the object and draw lines parallel to the walls from the center of the object. Let me just put this line in here. There. And now I'm gonna draw one straight across to get my triangle. And there is my two 45-degree right angle triangles. And I'll draw the line straight down here. There we are. So now we have half of 36, which is 18 plus 16, which is 34. So if the rise is 34, then my run is also 34. So this measurement that I have in here is equal to 68. Okay. Now I'm going to draw another right angle triangle because we have to solve for this piece right here. This piece right here is my travel, and here is my right angle triangle on that. So what we have to do is we have to get the measurement from the red line to the wall. Right here, I need this measurement. And this measurement just happens to be 18. This is half of this circle plus 15. So this blue line right here is equal to 33. And now, as you can see over here, I have 12 inches from this line to the wall is 12. So I'll minus it off of 33. 12 minus 33 is 21. So this line right here, I'm going to make it black now. This line is 21. And if I had a rise or a run of 21, I simply multiply by 1.414, and that would give me the travel of this line. So this line is equal to 29.694. Now I will solve for this particular piece down here at the bottom, and I'll draw my right angle triangle right there. There it is right there. Now I should have said something before I started this. This is NTS. Does everybody know what NTS means?
Not
to scale.
None of these are to scale. So having a look at it, you're saying that line is not 21, Doug, 21 inches. Of course it's not. It doesn't look like it, but mathematically it is. So it's not to scale. So here's our right angle triangle. We're solving for this little travel right here. We get the measurement from the red line to the wall. And this is 18, half of this diameter, plus 11. So this is 29. And now I minus off 14 off of the 29, which makes this line 15 inches. So to get the travel of that, I go 15 times 1.414. And that equals 21.21. So this line is 21.21. And now I add these together. So that's 21.21 plus 68 plus 29.694. And that would be my dimension there.
118.9.
29.694, thank you, is 118.9. Is dimension unknown. JJ, would it help if I did more examples?
No, I think I'm getting the hang of it. I'm pretty good with this stuff anyways, but like this one, if I would have seen that question, I would have had no idea. So I just
Okay,
wanted to
well,
be able to reflect back. But we've got those old modules too. Is there stuff on this in there?
100%.
Okay.
In the review, first year review, under the content in D2L, you will find all of the ILMs, all of the math ILMs from first year. Yes, and one of them is 45-degree offsets. Correct.
Okay. Yeah, perfect. Yeah, that's good enough.
Can you do another one?
Yes.
That went over my head.
Absolutely, I will do one more.
Or can you put like step one, step two,
Sure.
like where you get all the measurements? Yeah.
Yep. Yep, I will. Let's see what else I can do. I got lots here, so. Like you don't see pictures of Doug in here. I think these are all rolling offsets, I think. And okay, I'll do another one of those, Pat, in a minute. Let's just do this one here. I know this one looks pretty crazy, but this is still using, you got to remember the 1.414, okay, on these right angle triangles. So first off, let's solve for A. And I can do A by simply drawing myself a right angle triangle right in here. Here's my right angle triangle on A. So this measurement here says 40. This one says 20. So that makes this line right in here 20. It also makes this rise 20. Rise and run are always the same on a right angle 45-degree triangle. So A is equal to 20 times 1.414. So A is equal to 28.28. And now I can get B in here because you can see that this measurement over here is 30. And if I know that this is 20, this line right over here is 20, 30 minus 20, B is equal to 10. Now I'm going to solve for C. I'll use a different color. This is the travel for C. I'm going to draw a right angle triangle in here. There it is. So I can go 40 plus 34, which is equal to 74, is to this line. And I will 20 plus 37, so this is 57 from the wall to here, or to here, sorry. And I will simply minus these off. 74 minus 57 is equal to 17. So this line is 17. This line has to be 17. So C is equal to 17 times 1.414. And that equals 24.038. Am I correct on this? 57? Yeah. And now I can see that 30 is right here. So I can simply minus 30 minus 17. D is equal to 13. So the most important part in these triangles, in that a 45-degree right angle triangle, the rise and the run are always the same. The travel is 1.414 times longer. Okay, we're going to get back to another one of those with the objects in the corner. Let's see if I have PDF here. Okay, this is right out of the ILM. Let's do this one here. Okay, so in this one, we don't have the measurement from the corner. So where did Pat go? Pat, come back. Oh, you're there. Okay, we just can't see you. All right, so we don't have, wowzers, that just sprung right back. There we go. We don't have the measurement from the corner on this one. So we're going to start from the center of the object and draw a line parallel to the wall, another line parallel to the wall to get my 45-degree, two 45-degree right angle triangles. And there they are. Wow, that's pretty bad, but let me go back. This is pretty heavy. There we go. So half of 13 is 6.5. So 6.5 plus 6, that's a 6 in there, everybody. If you can't see that 6, that's a 6. Plus 6 is 12.5. So each one of these lines is 12.5, 12.5. So this measurement right in there is 25. Now I have to solve for this piece right here. And here's my right angle triangle right there. So we get the measurement from the red line to the wall. So half of 13 is 6.5 plus 6. This line is 12.5, and I'm going to minus 4. So 12.5 minus 4 is 8.5, and I can get the travel for that by just multiplying by 1.414. And that equals 12.019. So this line is 12.019 point. And now I need to solve for this piece right here. Here's my right angle triangle. There's the right angle. We're solving for the travel. We need the measurement from the line, the red line to the wall, which is 12.5 minus 6. So this line is 6.5. So we go 6.5 multiplied by 1.414. Is equal to 9.191. So this is 9.191, and now we add this and this and this together. And our total is 46.2 is our line X.
It wants the nearest 16th.
You want it to the nearest 16th?
Oh yeah, for X. So you
Okay, so
times two the
so that's
0.2 by 16.
46.20, what, 9? And so we take 0.209 inches. We want 16ths. We times that by 16. So that's 3/16. 46 and 3/16. Okay, so what I want you to do is see if you can figure out this question right here. The question that shows on your screen, it says, how much pipe could be saved if the offset in this picture were done with 45 degrees? So right now, as it stands, this piping arrangement is using 90s. So you can see the 90s here and here. So what if this is proposed? This dotted line is what we want to use, and I want to know how much pipe can we save if we use these. I know it's not a huge deal, but if this is 3-inch type L copper and you're keeping the scrap copper for yourself, you're going to want to save as much pipe as you can. So I'll give you a minute just to get started on this. If you got an answer, you could throw it in the chat. That's a, nope, you're just off, Jacob, too much. That's right, Jack. Give it to me in inches, though. Jacob, no, it's too less now. That's right, Steve. Deep, that's not correct. So let me just start off here. So this is our right angle triangle right here, as you can see. So if we use the 90s, or if we continue with the 90s, that's right, Brian, I want to find out how much pipe is used with the 90s. So this 2'11" is equal to 35 inches. If this is 35 inches, then this measurement down here also has to be 35 inches. So if I use the 90s, I'm going to use 70 inches of pipe. Now, this is the proposed line right here. So to find out what that length is, I simply have to take 35 and multiply by 1.414. And that equals 49.49. So this goes 70 inches if I use the 90s, but if I go this way, I'm only using 49.49. So I'll minus 49.49 off of the 70, and that's going to be 20.51 inches of pipe saved if I use 45s. And this is where it really has some good application for us, is when we use 45s instead of 90s. You also get better flow, better laminar flow in that piping system if you use 45s rather than 90s. Less friction loss in that. Okay. I think we should do some more examples. I don't want to insert that. I want to insert a Word document. Okay, can everybody see that offset that we have there? Okay, we're going to do a couple of these questions. So I have some measurements down at the bottom here. It says A is 22, and it says B is 10. Now, these are 45s, and I want to find out the offset. So listen, the offset is measured how much the pipe is offset. So this measurement, so if I draw a right angle triangle right here, this measurement from here to here is the offset or the set, is it not? I think I told you that before. So 22 minus 10 gives me my offset of 12. Now to find the travel, that's this measurement right here, to find the travel, and if I had a rise or a run or an offset, I could simply take that 12 and multiply it by 1.414 to give me my center to center travel, which is 16.96. Now, you guys should already know, oh, why does that pop up? You should already know that the throw minus the engagement is equal to the fitting allowance. That's a little throwback from first year as well. Throw minus engagement is equal to fitting allowance. Now, we could use our IPT trade handbook to actually account for this, but I'm giving you these numbers because just for math's sake. So what is my end-to-end travel then? If I have my center to center of 16.96, what is my end-to-end travel?
14.96.
That's right. How many fittings do I have?
2.
2. So my end-to-end travel is then 14.96. Because I have to take 2 fitting allowances off of that travel. Let me just erase these ones and we'll go to the next one here. So now we have the next measurement. A is 35, B is 18. So what is my
17.
offset? It's pretty easy. 17, is it not? Yeah, my offset right here is 17. And now I can find my center to center travel by taking 17 and multiplying it by 1.414. So the travel comes out to 24.038. And then in this regard, the throw minus the engagement is my fitting allowance. So now my end-to-end travel is I take off 2 fittings is going to be 23.038. We'll do the next one on this list here. So we have A at 490 millimeters, B at 250 millimeters. So I could find my offset by taking 490 minus 250, and that equals 240. And I can find the travel now by taking 240 and multiplying it by 1.414. And that equals 339.36. My throw is 25, my engagement is 15, so my fitting allowance is 10 millimeters. I take 2 of them off of there. So that means 319.36 is my end-to-end travel. Okay, kind of cool. I'm going to share my screen again, and we're going to talk a little bit about the rise and the run on a 45-degree triangle, and we're going to do a 22.5-degree triangle. So there's a right angle triangle. In a 45-degree right angle triangle, whoa, why does that do that to me? I keep pressing the little button on the side of my pen, and it does it. So trigonometry would say you take the side adjacent to the angle. So this is the side adjacent. or we know it as the run. And if it's a 45-degree, we multiply by 45 tangent, and that would equal to the rise. So in your calculator, I want you to hit 45 and hit the tan button. 45 tan. Does anybody have that number?
1.
1.
1. So the run times 1 is the rise, meaning the run and the rise are always the same in a 45-degree right angle triangle using trigonometry. So similarly, if I had a different angle in there, for example, if I had a 22.5. So when I cut a 45, if I go 45 and I divide it by 2, that's going to equal 22.5. Is that right? So we're going to use this number moving forward as well. So we're going to have the run, and if we multiply that by 22.510, that would equal the rise. That would equal this line right here. So type in 22.510 in your calculator. It should come out to 0.414. Trigonometry would say that the tangent times the adjacent is equal to the opposite. And that's really the formula that I'm working with at this moment in trigonometry. So we're taking the adjacent, which is this line is the adjacent, and I'm multiplying it by the tangent of this angle, and that gives me the side opposite. So this is the side opposite. And this line is the side adjacent. And this equals A, this equals O, and this is the angle, and this equals T. And we'll solve for the hypotenuse as we move on in a little more involved in offsets, and we do all of the trig functions later on. I just wanted you to know the 22.5 number, because when we get to your project, as you can see, we take the 45s and we cut them in half to make 22.5-degree right angle triangles, so we can calculate all of these numbers. So that's going to be in shop class. Okay, so some of you may have already covered some of this stuff. Depends when you went to school. Because it was typically in first year, but now it has been moved to second year math. So we still have to go through it. So I'm going to go over it like it's your first time. You remember your first time, Riley? I don't know. Probably not. Oh, right. You didn't have a first time yet. I'm sorry. So this will be the first time. So that's. I'm talking about the ILM. I'm not. What are you?
Right. Yeah. That's totally what you're talking about, Doug. Thanks, bud.
So let's have a look at the objectives now. Just to give you guys an understanding, if anything you ever want to study anything out of any ILM, the first thing you should be looking for is the objectives. This is what you study. This is what you look at. If you need to study any ILM out of your books, you look at the objectives. The objectives are going to tell you what you need to know. All right. So that's the way you study these ILMs, look at the objectives, and then go through it. Now, there's a lot of information in these books, as you well know. I know you guys know that. So take your time and look at the objectives and then go through it. Okay, that's what we need to know. These objectives telling you perform temperature conversion calculations. Pretty easy stuff. We'll go over it really quick. We're going to state specific heat values for water and air. We're going to define latent heat, state the latent heat values for water, ice, steam, and propane. And we're going to do calculations of sensible and latent heat values. Okay, so that's what we need to do. And we might not get to all of them today, but that's okay. We're going to start. Okay, so this ILM is a basic understanding of heat and temperature, and it's really essential that you know this. This is part of our job. We live practically in the Arctic. Heat is important to us. Without heat, we'll all just die off in a very excruciating kind of thing. Okay, so let me go down to the next page here. Temperature and heat. Okay. Definition of heat. Heat always travels or flows from the hotter object to the cooler object. Pretty straightforward, right? So when my wife puts her ice cold feet against my legs, I can tell that the heat is leaving my body and going to hers, right? That's just the way it is. It just travels from the hotter to the cooler, okay? Until it reaches a uniform temperature, if it touches long enough. So then we have something about definitions of temperature. The measurement. Temperature is a measurement of kinetic energy or the amount of molecular movement. Do you see that there? Molecular movement is the measurement of temperature. So if you visualize a thermometer and it is filled with an alcohol-based liquid, as you heat it up, those molecules get excited and they start getting bigger. So as it gets heated up more, those molecules even get more excited and it gets bigger and bigger and bigger. So that's really the measurement of molecular movement, right? It's the George Costanza's law. Is everybody familiar with George Costanza's law? Is that if it's colder, it gets smaller. If it's warmer, it gets bigger. It's just the George Costanza law. And if you don't know what I'm talking about, just YouTube George Costanza in the pool, and you can figure out what that is. Okay. All right. So now it says in here that a cup of water and a bucket of water both have the same temperature. What has the most potential heat energy? Well, the one that has the greater amount of fluid in it will have more capacity for heat. That's really what they're saying there. Sources of heat. We have a bunch of different sources of heat. And one, I gotta move this little bar down at the bottom here. Hang on a second. There, get that over there. Sources of heat. Well, the sun is our principal source of heat, right? That's where we get all of our heat. We have other sources of heat, geothermal. If you live in Iceland, you will know what this means. Matthew, yes, that's right. So you know that exactly what I'm talking about, Matthew. Chemical reactions. Chemical reactions is burning. Burning natural gas is really a chemical reaction. So when we burn this hydrocarbon, we get a couple of things out of it. We get heat, we get light, we get, like, because of the flame, we get other gases, etc. So we get heat when we burn. We have nuclear reactions, electrical energy, and mechanical energy is the sources of heat that we have for us humans. I don't know too much else sources of heat. I mean, if you give grandpa a turkey sandwich and about an hour and a half later, he's going to be producing his own heat, but it's more of a different kind of methane gas, but you know what I mean. All right. Now, a thermometer is an instrument to measure temperature. We said we use a thermometer to measure molecular movement. Did I not say that? Yeah, I think I said that. Okay. And there it kind of talks about that for a second. So some thermometers have mercury in them. We don't use mercury anymore, do we? I hope not. It's something that you don't want to play with or anything like that. And then one of the temperatures we have is Celsius. And this guy, this Swedish physicist, Anders Celsius, set this up. And he put water and ice, and it was 0, and boiling water 100. Okay, that's pretty straightforward. I don't really need to talk about that too much, I don't think. And then there's, what do you call it? The next guy, Fahrenheit. Let me get to him. Daniel Fahrenheit figured that he used a combination of salt and ice to determine the 0 point. Ice was the freezing point, and when water boiled, it was the boiling point. Okay, so here's Fahrenheit, here's Celsius. These are very important numbers for you to remember. You need to know what the boiling point is in metric and imperial. You need to know what the boiling point is, 212 or 100, and the freezing point 32 and 0, not minus. So we need to know these, okay? And I think we already do. I mean, in retrospect, we should know those numbers. Now, here is the formulas to calculate temperature conversions. So if you're going from Fahrenheit to Celsius or Celsius to Fahrenheit, these are the two formulas you need to do that. Now I have an American vehicle, and all of the temperatures in the car is in Fahrenheit, right? So on my dash of my car, it will say it is 58 degrees Fahrenheit outside, right? So can somebody tell me what that is in Celsius? So we want to convert, we want to use this formula right here. So you take your degrees Fahrenheit minus 32. That's in a bracket. So you have to go 58 minus 32, hit the equals button.
14 degrees.
So that, okay, thank you for that. So that's 26. And then we divide that by 1.8. And that's 14 degrees C. Okay, pretty easy. Pretty straightforward. Now, let's do this. I have a temperature Celsius of 150 degrees C. I want to know what the Fahrenheit conversion of that is. So we'll use this formula up here. What you do is you take your Celsius, multiply it by 1.8, 1.8. Do that first. And then So that's 270, and then you add 32 to it.
Which is 302.
So anytime you're doing this, you got to remember that 100 degrees C is equal to 212 degrees Fahrenheit. So you have to make sure that you're kind of in that, or 0 degrees C is equal to 32 degrees Fahrenheit. So you can see by comparison if you're close.
How come they always use the 32 there in those formulas?
Listen, I didn't make the formula, but I don't know. It's just the way it is.
Could it be the same though as if you just use 0 degrees Celsius, or does it have to be the 32?
No, it has to be the 32. What if, Steve, this is a good question though. So what if, oh, I don't want to move the whole sheet. What if I had, let's do another one. If I had minus 10 degrees Fahrenheit and I wanted to change that into Celsius. So I want to know my Celsius down here. So I'm going to take this and minus 32 and then divide by 1.8. So this minus 10 minus 32 is how much? Minus 42.
That's 42.
And then I divide that by 1.8. Somebody do the math?
That'd be negative 23.333 repeating.
There you are. So it's important we use those numbers appropriately. Okay, Steve?
Thank you.
So minus 10 degrees Fahrenheit is equal to minus 23.3 degrees C. All right. And then look at this little image here. This is also important for us. Now, you see at this point right here where it says salt and ice? This is where the salt that they put on the road stops working. At minus 17.77 degrees Celsius, the salt that they put on the roads stops working, right? And it's ice. So then in this province, we put bloody gravel and boulders on the road for grip. And that's why I never have a windshield that lasts more than 2 months. I don't know. My windshield is always cracked because they put rocks on the damn road for traction, right? That's what they do here.
I thought we were murdering beets for that now.
Yeah, well, that only works to a certain temperature as well, Riley, right? That liquid, whatever they got, goo, you know, they pour that liquid, that pink stuff on the road now. I mean, whatever. I don't know what that's going to do to my car, but maybe it won't do anything. I'll probably sell it before then. Riley, you want to buy a car? Only kidding. Only kidding.
I own a truck. Sorry, buddy.
Okay. Look at this temperature. Minus 40 degrees Fahrenheit is equal to minus 40 degrees Celsius. This is where the temperatures actually come together. And down here, 460, absolute zero. Well, there's some numbers there if you want to know. But here, I want you to know this one here. Water is most dense at 39 degrees Fahrenheit or 4 degrees Celsius. That's a number that you should also know, that water is most dense. Now, I do want to talk about a little bit about water before I carry on here. Let me just see if I could draw a picture for you guys. I'm gonna draw some lines. And then I'll put some temperatures on here. So water is most dense at 4 degrees C or 39 degrees Fahrenheit. The freezing point is 32 degrees Fahrenheit or 0 degrees Celsius. This is the boiling point, which is 100 degrees Celsius or 212 degrees Fahrenheit. So I do want to explain that when water is most dense, it is the heaviest. That's when it is the heaviest. Now, if you dive down into a lake and the deeper you go, the colder it gets. That's where the cold water hangs out, is down near the bottom of that lake. That's where the coldest water is, down there. So I want to tell you that water expands slightly from 4 degrees C to 0 degrees C. It expands slightly. And then when it freezes, it expands 7.5% its volume. When water freezes, it expands 7.5% its volume. That's why it splits pipe. It splits copper pipe right down the seam of that copper because it expands and has nowhere to go, and it expands right in the copper pipe. And that's why it splits if it freezes in copper pipe. Now, I want you to tell you that water, as from 4 degrees C to the boiling point, at 100 degrees C, water expands as well. And it expands about 5% its volume. It expands about 5% its volume from where water is most dense to the boiling point. And this is the reason why we have expansion tanks in our heating systems. Okay, this is why we have expansion tanks, because we want the expansion to take place in the tank rather than our system. Okay, I can show you an image of that in a second. Now, when water goes from the boiling point to steam, it expands 1,700 times its volume. When it goes from water to steam, it expands again. Water expands when we freeze it, it expands when we heat it, and it expands when we turn it to steam. That shit just expands all the time. It's crazy. Okay. And let me go to this math thing. I'm going to show you this little heating thing. Trying to look at these resources here. Where are we? I don't think I have them loaded in here. Hang on a second. I just gotta go to a different course. Did everybody see the picture of the boiler there? This E right here, this is an expansion tank. And if I click on that, it shows a couple of pictures of expansion tanks. But what I want to get to is here. Let me just indicate right here, you see the 12 PSI gauge. There's my pressure. And if you look on the other side of the expansion tank, the pressure is still at 12 PSI. My temperature is currently at a 120. And inside my diaphragm expansion tank, it is also 12 PSI. So I'm going to start increasing the temperature of this water. So there's the temperature increasing. You can see the numbers climbing. And the expansion is now taking place in the tank, not in the system. So this is exactly how a diaphragm expansion tank works in a heating system, because we don't want that expansion to take place in our system out here. Okay, pretty cool.
Doug, is that something we can look up on D2L and have like a video like that ourselves? Kind of.
Yes, you can. Now, the only problem is that that is a shockwave file. So it's an SWF file, which is no longer supported. So I have an older browser. I have Internet Explorer browser that I use so I can view it. If you go into Blueprint Reading and you go into resources, you will see first year and second year media resources, and all of those flash pieces, those SWF files, shockwave files, are all there.
Awesome. Thank you.
Okay. Where am I now? I'm going to stop sharing for a second, and I'm going to pause. All right, and I'm going to share my screen again. So we talked about a bunch of these things already. So we're going to go right into this next one where it says difference between temperature and temperature change. Now, I'm not going to put a lot of stock into what they say here about these two examples. These two examples just end up confusing me a little bit. So what I want to talk about is this right here, delta T. Delta T is basically what we have to classify temperature change. We want to know the difference between the temperatures. So for example, if I had some water at 50 degrees Fahrenheit and I increase the temperature of that water to 85 degrees Fahrenheit, the temperature difference between these two is 35 degrees. So that would be known as my delta T. It's the temperature difference, okay, between these 2 points. Or if I give another example of this, if I go minus 15 degrees C to 120 degrees C, what is the temperature difference between these two? And that's going to be 135 degrees C is the delta T. So it's the temperature difference between the start and the finish, okay, is what delta T means. Now we have a table in here, and these are nice to know temperatures. Body temperature, 37 degrees C is normal body temperature, not for my wife. She's a lot colder than that. I don't know why, but she is. Room temperature. Okay, we got to be careful about this room temperature thing. for some people, that is not warm enough. If we're designing, say, a retirement center, that room temperature design would be probably a little bit higher than that. Okay, my wife all of the time likes to jack this temperature up quite a bit on the thermostat, but I keep turning it down. I have this, what's really nice thing I have is I have the, it loads here. I have this on my phone. You can see that. So I could change the
Went all
temperature.
Bluetooth today, Doug.
Yeah, I could change the temperature of the house on my phone, so my wife can turn up the heat as much as she wants. And I can just change it back. And then when she says she's still cold, I say, put on a sweater. And that way, everything is good, right? Put some socks on. Jeez, it's winter. All right, just kidding. Just playing around. Okay, so the next important temperature is a hot water heating setting. 140 degrees Fahrenheit is a standard setting for your hot water tank. Why do we have to get the temperature up that high? Does anybody know?
Oh, you don't burn people.
Bacteria growth.
There's a lot of different reasons. One of them is we don't really want to increase that by too much because you can scald people, right? So now it is by code that any shower valve or combination tub shower valve has to have some kind of positive temperature setting or posi-temp, so you don't, or anti-scald device put in there so we don't scald people. Another reason, if we have temperatures less than 140 degrees C and it ceases to be moving water. So say you go on vacation for 3 weeks and your hot water tank is sitting at 120 degrees, it has the opportunity to create bacteria inside that tank. It's nice, warm atmosphere, no water's flowing. And what we end up doing is you could have something called Legionnaire's disease. And it's a bacteria that we can get. It can make you sick. It typically doesn't kill anybody, but it can make you sick and ill, like flu-like symptoms. So I would suggest if you go on holidays, the first thing you do when you get back is put your laundry in. Get that water in that hot water tank moving, get that burner burning, and get that water heated, okay? The first thing a lot of people do is they take a shower when they come home. And then I don't know what they're doing in there, but they're brushing their teeth or drinking the water or whatever. And if that water has that bacteria in it, you're ingesting it. So this is what I suggest, get that hot water tank fired and working, that sort of thing, and then you'll be good to go, okay?
Doesn't the 140 also have to do with TDS?
TDF,
S.
total dissolved solids?
Like, doesn't it have to do with like settlement in the tank?
TDS is total dissolved solids. There is a little bit of theory behind that, Hemian, and that is where scale will start to settle out. And if you have a high mineral content in your water, then anything around 140 or less, you're going to get scale coming out, or even hotter, you're going to get scale. That's where that white scale comes on our aerators and on the end of our taps, or that inside the hot water tanks, you get that scale. It's all the minerals that are in there, and they react when they get to that kind of temperatures as well. We're not going to concern ourselves with that yet. We'll talk about that in our future math courses, okay? Is that cool? And then this last one right here, max temperature for a low pressure steam boiler, and the max pressure is 15 PSI, and that's just the max temperature for that. So those are nice to know temperatures. Who knew we were going to get all that information out of that? So now it brings us to objective 2. And then they start talking about heat. And heat is what we need to know. Now, they talk about kilojoules and British thermal units in here. We're not going to talk about changing of state, not yet. We're going to get there, but not yet. First off, units of measurement of heat energy. So a BTU, and here's the definition of that BTU. Remember we said this already? 1 BTU is the amount of heat to change 1 pound of water by 1 degree Fahrenheit. There it is. 1 BTU is the amount of heat required to change the temperature of 1 pound of water by 1 degree. A kilojoule, it's just a metric measurement of a BTU. A BTU is imperial measurement. A kilojoule is metric measurement. And they say it takes 4.2 kilojoules to raise 1 kilogram of water by 1 degree Celsius. Okay, so that's really a metric equivalent of a BTU, but we're using a kilogram and a degree Celsius. So it takes 4.2 kilojoules to do that. Now, this is where it starts getting important. Sensible heat. Sensible heat, by definition, is the amount of heat to change the temperature only. It's the amount of heat to change the temperature of a substance only. We're just warming it up, is all we're doing, and that is called sensible heat. Okay, when you warm something up, sensible heat. This next thing called specific heat capacity. Specific heat capacity, they have a definition down here at the bottom. The specific heat capacity of a substance is the quantity of heat required to change the temperature of 1 unit of mass by 1 degree. Okay, so this is going to be a multiplier. We use specific heat capacity and we use the numbers associated with it for a formula to calculate sensible heat. And I'm going to, over here, this gives us a list of sensible heat. This is a table of specific heat capacities. So water has a specific heat capacity of 1 BTU per pound per degree Fahrenheit. These are our multipliers. And similarly, there's a metric conversion to that, and that's 4.2 kilojoules per kilogram per degree Celsius. And here's where I'm going to give you a formula triangle. Heat, and when I say heat, I'm going to say BTUs or kilojoules. That's what we measure heat in. So the heat is equal to the mass, and mass has to be either pounds or kilograms, is equal to mass times the delta T. So delta T is the temperature difference times the specific heat capacity of the substance we're using. So the specific heat capacity is these numbers. If I'm talking about water, it's 1 BTU per pound per degree Fahrenheit, or metric 4.2 kilojoules per kilogram per degree Celsius. If I'm talking about a substance like ice, look at this, ice right up here, it's 0.5 BTUs per pound per degree Fahrenheit. If I'm talking about steam, it is 0.5 BTUs per pound per degree Fahrenheit. So this list, this table gives us our substances. And it gives us our multiplier. And this specific heat capacity right in here, let me make it red. This specific heat capacity is our multiplier, and then they give us our numbers in here. So these are our numbers that we need to then calculate a sensible heat equation. For example, if I had a hot water tank, and it was 33 US gallon hot water tank. Okay, 33 gallon US hot water tank. And I filled it up. It's brand new. I installed this 33 gallon US gallon hot water tank, and I filled it up with water. And the water here in Calgary, if you don't know, it is pretty darn cold. So I'm going to say that that water was 50 degrees Fahrenheit when I filled up that tank. I want to increase that temperature to normal operating temperature of a hot water tank, which is 140 degrees Fahrenheit. I want to know how much heat does it take to heat this water. So using our formula triangle, the one that's up here, it says take your mass times it by your delta T times it by your specific heat capacity is equal to the heat. So we have to first find our mass. We have a gallon capacity in here, and it says 33 US gallons, but my mass needs to be in pounds. So I gotta go 33 times 8.33 pounds in a gallon. And that comes out to 274.89 pounds. So now I take my mass, 274.89 pounds. And I'm going to multiply it by my delta T. My delta T in here is from 50 to 140. So my delta T is 90 degrees Fahrenheit. And then I'm going to multiply that by the specific heat capacity of this substance. This is water. Water says it has a specific heat capacity of 1 BTU per pound per degree Fahrenheit. And as I multiply these through, the pounds get knocked off, the Fahrenheit get canceled out as well, and I'm left with BTUs. And it takes 24740.1, 24,740 BTUs to increase that temperature of water from 50 to 140 degrees. Give you a minute to copy that example down if you're doing that.
Doug?
Yeah.
Sorry, where did that 8.33 come from again?
That is the mass of 1 US gallon. So this is the mass of 1 US gallon. I have 33 US gallons. Remember what I said up here, that your mass in this formula, the mass has to be either in pounds or kilograms.
Oh, okay.
To change the gallons into pounds. And that's what 1 US gallon weighs.
There's some stuff that Doug posted, like formula sheets and weights and measurements and stuff on D2L, and I suggest everyone print those out and just have them beside you.
Good point, JJ. Thank you. Okay, let's do another example of this, okay? Let me pull one over here. So we're heating some water. In a boiler, if I start off at 120 degree Fahrenheit water, and I want to increase that boiler water to 180 degrees Fahrenheit. This boiler happens to hold 80 imperial gallons. I'm going to know how much heat does it take to heat this water. So our formula triangle is the heat is equal to the mass times delta T times specific heat capacity. So we have 80 imperial gallons. So our mass is 80 gallons times 10 pounds per gallon. So that's 800 pounds of water. So 800 pounds multiplied by my delta T from 120 to 180. That's a 60 degree delta T. This is heating water. So my specific heat capacity, or my multiplier, is 1 BTU per pound per degree Fahrenheit.
The answer is 48,000.
That's right. It takes 48,000 BTUs just to get that temperature up to 180 degrees. So we're just warming up the water to 180. That's it. Now, before, I remember, so if I just wanted to expand on this, I told you that 1 cubic foot of CH4 is 1,000 BTUs. Or I could say that there is 1,000 BTUs per cubic foot of natural gas. Right? That's how many BTUs I get out of 1 cubic foot. So I could say, how many cubic feet of gas do I have to burn to get 48,000 BTUs? I simply divide by 1,000 BTUs per cubic foot CH4, and that equals 48 cubic feet of natural gas I need to burn to get that heated. So we could take one question and we could ask many, many more on that same question. Because then I could say that that boiler has an input of 56,000 BTUs per hour. And I'm going to ask, how many hours does it take to get that temperature of water up there to that height, to that temperature? Then I would go divided by 48 thousand BTUs it takes. So 48,000 divided by 56,000 is equal to 0.857 hours. So just under an hour for that boiler to get that water up to that temperature.
And that boiler would be 85% efficiency then.
Well, no. It might, we don't know that yet, Brandon, because this is just how many BTUs it takes to get that water. Now, if that boiler was less efficient, then I would have to use a different number. So if the input of that boiler was 56,000, and if I said that boiler was only 70% efficient, which means 56,000 times 0.7, it means I'm only going to get 39,200 BTUs per hour into the water. So then it'd be 48,000 divided by 39,200. So it's going to take over an hour to get that water up there.
Sorry, where did you get 40 or 56,000 from?
I just told you that I had an
Oh, okay.
appliance with an input of 56,000. I just pulled that out of the air.
Okay.
So a little deeper than that on the efficiency side, Brandon. Is that pretty good? Do you guys understand how sensible heat is and what it is? And how to calculate it? Do you need more examples?
I'm down for more examples just for practice.
Sure.
No, I get it for the most part. Down for more practice.
Okay, let's do another example here, and we'll do one in metric, right? Let's do a metric example. So using our formula, I keep on writing the formula because I kind of want you to remember it. So the heat is equal to the mass times the delta T times the specific heat capacity.
We can't see your screen.
Oh, let me share my screen. Thank you for that. So now I'm going to say I have 700. I said I was going to do this metric. 700 cubic meters of water. That's a lot of water, like a big swimming pool. And I want to heat that water from 50 degrees Fahrenheit to a nice swimming pool temperature to 80 degrees Fahrenheit. How much heat does it take? So, sensible heat equation would say take my mass. So I have 700 cubic meters of water. So 700 meters cubed. How many kilograms of water in 1 cubic meter? Does anybody remember?
1,000.
It's 1,000 times 1,000 kilograms per cubic meter. That gives me a lot of kilograms. That's a big swimming pool. I got a lot of water in there. And now I'm going to take my delta T. This should be Celsius, by the way. I don't know why I put Fahrenheit there. That's going to be hot water, but that's okay. It's just math. Times my delta T times the specific heat capacity of water. This is metric. It's a different number. 4.2 kilograms, or excuse me, kilojoules per kilogram per degree Celsius. So let me type that out. 700,000 times 30 times 4.2. So this is going to equal 88,200,000 kilojoules to warm up that swimming pool full of water. It's going to take a long time to do that. Let me give you another question. I'm going to say 30 kilograms of water was heated with 3,000 kilojoules. What is the delta T? So anytime I do this, I want to know my formula triangle where the heat is equal to the mass times the delta T times the specific heat capacity. Now, these formula triangles are amazing in this way where if I want to know what the delta T is, I simply take it out of the equation and I do what's left. So it says the heat divided by the mass times the specific heat capacity would equal my delta T. So this is the equation now. 3,000 kilojoules is my heat. And I will divide that by my mass times my specific heat capacity. And if I do this, the kilograms get canceled out, the kilojoules get canceled out, and I'm left with the degrees Celsius. So what is your delta T?
420.
No,
23.81.
it's 23.8 degrees Celsius is the answer. And remember, down here at the bottom, I have to multiply that first.
Head mass.
So yeah, so it's going to be 3,000 kilojoules divided by, what is it, 120?
6.
Yeah,
126.
126. And that's going to be kilojoules per degree Celsius because the kilograms get canceled out. And I'm left with degrees C. Okay. Awesome. That's fun. So the next example is I have steam at 240
Your screen
degrees.
is not showing.
Okay,
Oh
yeah,
yeah,
the
I
screen.
keep forgetting to share. Thank you for that. I'm glad you speak up. It's important. So I have steam at 240 degrees Fahrenheit. I want to get this steam to 350 degrees Fahrenheit. So I have a substance and I'm just raising the temperature. So this is a sensible heat equation. And I'm going to tell you that I have 800 pounds of this steam. Okay. So the heat is equal to the mass times the delta T times the specific heat capacity. So we have 800 pounds of steam. And I'm going to multiply that by my delta T. My delta T right here is 110 degrees Fahrenheit. And I'm going to multiply that by the specific heat capacity of steam. And steam is 0.5 BTUs per pound per degree Fahrenheit.
$44,000 BTU.
That is correct. 44,000 BTUs it takes to heat that steam a little hotter, right? So we get nice hot steam then. Excellent. So the next question is, we have 4 kilograms of ice at minus 17 degrees Celsius. And I want to heat this up to 0 degrees Celsius. I'm just heating it up to the melting point. How much heat does it take? So in this example, we have 4 kilograms of ice. So I need to find, I already have my mass. So it says mass, 4 kilograms, multiplied by my delta T. My delta T is 17 degrees Celsius. And I have to multiply that by the specific heat capacity of ice in metric. What is that number?
And 36.
Actually, the specific heat capacity of ice in metric is 2. Go back to that table in your book. It is 2 kilojoules per kilogram per degree Celsius. And that equals, yes, Alexander, you're exactly right, 136 kilojoules.